In this module, we will discuss the topic of diffusion. Diffusion is the macroscopic transport of substances driven by concentration differences across the system. These concentration differences create a non-equilibrium state. As a response, particles of matter start to move spontaneously from regions of higher concentration to regions of lower concentration and redistribute themselves to even out the concentration differences. This process, diffusion, reflects a natural tendency towards achieving a uniform distribution of particles, which is a characteristic aspect of equilibrium. To continue our discussion of diffusion, understanding the mathematical concept of the gradient of a three-dimensional function is crucial. The gradient provides a quantitative measure of how a system property, such as the concentration of a certain substance, changes in space. Let's consider specifically the concentration of a certain substance at any point in a medium in a three-dimensional Cartesian coordinate system x, y, and z. Mathematically, the gradient of concentration is a vector given by this equation, or alternatively using base vectors by this equation. Here, dc by dx, dc by dy, dc by dz are the partial derivatives of the concentration function with respect to x, y, and z respectively. These derivatives represent the slope of the concentration change along each axis. All in all, the equations indicate that the component of the gradient vector along each coordinate axis is equal to the partial derivative of the function with respect to the variable of that axis. The concentration gradient has the following properties. It is a vector that points in the direction of the greatest increase in the concentration. Its magnitude is the slope of the concentration increase in that direction. Thus, the gradient of concentration as a function of coordinates x, y, z characterizes and quantifies how the concentration is distributed in a three-dimensional space of a system. The tendency of substances to spread in gases, liquids, and solids can be understood from multiple perspectives, including thermodynamics. From the thermodynamic viewpoint, diffusion aligns with the second law of thermodynamics, which states that global entropy tends to increase. When temperature and pressure are constant, this global increase in entropy is equivalent to a decrease in Gibbs energy. In terms of thermodynamics, a spatial gradient in concentration also represents a gradient in chemical potential. The system naturally seeks to reach equilibrium by eliminating this gradient. Therefore, diffusion can be defined as the spontaneous macroscopic transport of substances driven by a gradient in chemical potential. This process is a fundamental aspect of achieving equilibrium in a system, as it works to balance out the uneven distribution of particles and their associated chemical potentials. Fick's first law of diffusion describes the relationship between the diffusive flux of matter and the concentration gradient. It is expressed by this equation. Vector J equals negative of d times the gradient of concentration. This law, as expressed by this equation, states two relationships. First, the negative sign in the equation indicates mathematically that the direction of the diffusing flux is the opposite of the concentration gradient direction. Physically, matter naturally flows from regions of higher concentration to regions of lower concentration. Therefore, while the gradient vector, according to its mathematical definition, is directed from lower to higher concentration regions, the flux vector is directed from higher to lower concentration regions. This figure illustrates the relationship between the directions of the diffusive flux and of the concentration gradient in a one-dimensional example. Here we see that the concentration decreases as the distance x increases. The concentration gradient, which in this case is just equal to the derivative of concentration with respect to distance x, is negative. As a result, the diffusive flux of matter is positive, indicating its movement towards longer distances x. Furthermore, Fick's first law of diffusion states that the magnitude of the diffusive flux in a medium is proportional to the magnitude of the concentration gradient within that medium. It means that diffusion fluxes are stronger when there is a steeper variation in concentration, or in other words, a significant change in concentration over a short distance. This is because there is a stronger driving force for the particles to move from a region of higher concentration to a region of lower concentration. Conversely, if the concentration is nearly uniform across the medium, there is almost no net flux of particles. This is because there is no significant gradient to drive the diffusion. The coefficient of proportionality between the magnitudes of the diffusive flux and of the concentration gradient in Fick's first law is represented by the diffusion coefficient d. To deduce the dimension of the diffusion coefficient d, we need to first understand the dimensions of both the flux and the concentration gradient. Flux is defined as the amount of substance that passes through a unit area per unit time. The dimension of flux is therefore time in the power of -1 multiplied by length in the power of -2 multiplied by the amount of substance in the power of 1. A concentration gradient is a change in concentration over a distance. Concentration itself has the dimension of length in the power of -3 multiplied by the amount of substance in the power of 1. Therefore, the dimension of a concentration gradient is length in the power of -4 multiplied by the amount of substance in the power of 1. The dimension of d is the ratio of dimensions of flux and of concentration gradient. By inserting the respective expressions, we deduce that the dimension of the diffusion coefficient is time in the power of -1 multiplied by length in the power of 2. The respective coherent SI unit of the diffusion coefficient d is square meter per second. The diffusion coefficient, denoted as d, is a key parameter of diffusion processes. It quantifies how rapidly a given substance diffuses within a given medium. The magnitude of d is influenced by several factors, including the size of the diffusing particles and the properties of the medium, particularly its viscosity and temperature. From a thermodynamic perspective, the force driving diffusion behaves similarly to a physical force. It accelerates diffusing molecules until there is a balance between this driving force and the viscous resistance exerted by the medium. Once this balance is reached, the molecules achieve a steady drift speed. This balance between the driving force and the viscous resistance is the key to linking the diffusion coefficient to the system's properties. An equation that relates the diffusion coefficient to the physical properties of the system is the Stokes-Einstein equation. This equation is given by D equals kBT over 6p eta R. Here, Kb is the Boltzmann constant, T is the absolute temperature, eta is the dynamic viscosity of the medium. R is the theoretical radius of a spherical particle as considered by the respective model. For real particles, R is an effective size called hydrodynamic radius. This equation explicitly shows that D is inversely proportional to the dynamic viscosity of the medium. It is also inversely proportional to the hydrodynamic radius of the particle R. It suggests that the higher the viscosity of the medium and the bigger the size of the particles, the slower the diffusion rate of the particles in this medium. Fick's second law of diffusion provides a comprehensive framework for understanding the dynamics of diffusion processes in three-dimensional space. Mathematically, it is expressed by what is often referred to as the diffusion equation. Here, delta represents the Laplace operator, a critical component in this equation. In a three-dimensional Cartesian coordinate system, the Laplace operator is defined as the sum of all unmixed second partial derivatives. The Laplace operator quantifies the curvature of the concentration in all three spatial dimensions. Fick's second law of diffusion essentially states that the rate of concentration change with time at any point in space, including its sign, is proportional to the curvature of the concentration at that point. To make this concept more tangible, let's consider a one-dimensional example of concentration distribution. In regions where the curvature of the concentration gradient is positive, indicating a trough, the concentration tends to increase over time, leading to the filling of the trough. Conversely, in regions where the curvature is negative, indicating a peak, the concentration tends to decrease over time, causing the peak to spread out. If the curvature is zero, indicating a linear concentration profile, there is no change in concentration over time at that point. This one-dimensional example helps illustrate how Fick's second law governs the diffusion process, driving the system towards a state of equilibrium by smoothing out concentration irregularities over time. To conclude this module, let us consider a special case of stationary or linear diffusion. This occurs when the concentration varies linearly across a certain region of space. Consider this illustration of a concentration profile, concentration C as a function of position x. Here, the concentration changes linearly from the value C1 at point x1 to C2 at x2. In this case, the magnitude of the concentration gradient is constant between x1 and x2 and equals the ratio of concentration change over the position change. The flux is also constant. Its magnitude equals the product of diffusion coefficient D and the gradient of concentration. Now, the second derivative of concentration with respect to position in this case is zero at any point. Consequently, according to Fick's second law, the rate of change of concentration with respect to time is also zero at any point. What does this mean? It implies that the concentration within this region does not change over time. The diffusion takes place in a stationary state, despite the ongoing movement of particles from the region of higher to that of a lower concentration. The overall concentration profile remains unchanged. This stationary diffusion is an important example of diffusion processes and is necessary for understanding certain steady-state processes.